This is a visual presentation of our Samara seed project. To start, we're going to introduce auto-rotation, then go into our experimental methodology, then go to our problem formulation, then the theoretical analysis, and then the zero torque condition. And then further in the project, we're going to collect the final experimental results and then conduct a comprehensive analysis to compare these measured values to our theoretical predictions. So to introduce auto-rotation is a key aerodynamic principle that is seen when rotor blades spin naturally due to vertical airflow, and this allows for controlled descent without engine power. The Samara seed uses this principle of auto-rotation for maximum dispersal distance, acting as a single-bladed rotor. This helps to show that flight is governed by a few fundamental aerodynamic parameters, which we will identify and quantify. So our experimental methodology, our primary objective was to investigate and quantify the characteristics that affect descent time. So for our measurements, we used a digital scale that is accurate to 0.01 grams, and we used rulers for measurements like chord and radius. And then for the drop procedure, we dropped 5 unique Samara seeds, and we did 5 drop trials per seed, and each was dropped from a height of 10 feet. And then we did an extra test by adding mass in the form of tape to one of these seeds and observed how it affected the descent time. So the problem formulation and governing variables. So to model this, we treat the Samara seed wing similar to an airfoil, and then we establish common terms such as leading edge, trailing edge, and center of gravity, as you can see in the picture. Then we create a force balance, and then we assume that the flight is in a steady state where the upward lift is balanced by the downward weight. And then our governing variables would be these 6 parameters, which is the chord length, the radius of the wing, the angular velocity, the mass of the seed, the dynamic viscosity, and the air density. So for our theoretical analysis, our purpose is to reduce these 6 variables and the 3 dimensions of mass, length, and time to 3 non-dimensional parameters or pi terms. And so when we did this Buckingham pi analysis, we got some key results. One is the pi 2 is equal to c over r, and this is the inverse aspect ratio, and that shows that the wing's physical shape directly impacts its descent time. And then the other term we got is 1 over the third pi, and that is equal to the weight over the density times the gravity times r to the third. And this relates the wing loading or the ratio of weight to the rotational dynamic pressure. These results show that the descent is primarily influenced by the geometry and the pressure to weight ratio acting on the wing. And then the zero torque condition is assuming steady auto rotation. The seed is falling at a constant velocity vt and spinning at a constant angular velocity, which is omega. And then so the condition 1 is that the thrust to lift, the thrust and the lift or the lift is equal to the weight. And then condition 2 is the total aerodynamic torque, or Q, is equal to 0. And then we use blade element theory with simplifying assumptions, which are small induced velocity, constant coefficients, and small angles. And then the key relationship we get from the ratio of these forces is that the tangent of phi is equal to the coefficient of drag over the coefficient of lift. And then by relating this to the ratio of speeds, we derive Vt over omega r is equal to Cd over Cl.
Moving on to the data that we collected through the trials, on the right side, we have the time trials and the time it takes to descend the seed to descend 10 feet. As well, on the left side, we have the physical measurements of the seeds and the wings. Moving on to, that wasn't really what I want. Moving on to the data collected during the experiment, on the right side, we have the time trials in which how long it takes the Samara seed to descend 10 feet, and on the left side, the physical measurements of the seeds. Using this data, we're able to come to certain conclusions. Firstly, starting with mass, as we plot the mass versus time plot, there is a decreasing trend where as mass increases, time decreases. Furthermore, We can further prove this by creating a controlled experiment where mass is the only variable using C2. On the left side of the table are the times of the unweighted C2, where then we added weight to the experiment and the times for C2 descent significantly decreased. Both of these solidify the point that mass heavily contributes to decreased descent times. Here we have the C2 trial videos displaying this in action. On the left, we have the C2 trial with no additional weight put on, whereas on the right side, we have weight put on, and we can see a significant decrease in the time it takes the Samara seed to reach the ground. Moving on to the cord, we're able to see that as chord increases, the time for descent increases as well. This can be attributed to the fact that with a longer chord, there is more area for lift to be produced. This lift force being produced allows it to counteract the weight force pulling the Samara seed down and keeping the Samara seed in the air for longer. Moving on to the span, however, we see that a longer span decreases the descent time. This challenges the previous statement of more area generating more lift, keeping the Samara seed in the air. This is because as the span increases, weight also increases. However, as weight increases, it actually affects the force on the overall Samara seed more than the lift being generated by a longer span. Because this weight generates more downward force than lift applied on the Samara seed, the weight counteracts the lift being produced by a longer span and actually pulls down the seed faster, decreasing the descent time. Moving on to aspect ratio, we see as the aspect ratio increases, the time of descent decreases. This further proves this previous statements made about the chord and the span of the wing, and also signifies how a shorter, thicker wing is more beneficial in a Samara seed maintaining airtime. Once again, this is because the span brings more weight per area or wing loading, therefore increasing more downward force on the Samara seed rather than generating more lift to keep the Samara seed in the air. Moving on to Ben.
So moving on to the airfoil lift theory, we went over in class a lot of different explanations for how wings generate lift. We arrived at the correct one being that wings generate lift by causing pressure difference on the upper and lower surface with a higher pressure on the lower surface generating the lift. So we move this to the 2D thin airfoil theory, which assumes steady 2D incompressible and irrotational flow to add some simplifications to how we can model how a wing generates lift. There's constant velocity along the span, so no rotation. Symmetric airfoil has the coefficient of lift formula provided here. And it's important to note that for cambered airfoils, they will produce lift at an alpha of 0 or angle of attack of 0. So why the airfoil theory is great to predict lift, it breaks ultimately when we compare it to the Samara seed. The Samara seed isn't in a free stream. It creates its own flow via rotation. So the local velocity varies along the radius with the formula V relative equals omega r. This creates a non-uniform lift distribution along the wing. Also, the Reynolds number also varies along the span. The inner region has a lower Reynolds number where it's viscous dominated versus the tip that has a higher Reynolds number, which has more lift. Both of these violate the constant Reynolds number and 2D flow assumption that the thin airfoil theory provide us with. Additionally, natural camber matters. Samara seeds produce lift even at near zero angle of attack. However, it's in an unsteady rotating flow field. They also have a leading edge vortex. Rotation and spanwise flow stabilize a leading edge vortex on the seed, which increase circulation and delays stall, a behavior that's not predicted by the thin airfoil theory. Additionally, the flow is unsteady in 3D, which causes continuous rotation, which results in a continuous changing velocity field. And the thin airfoil theory assumes that with steady 2D flow, there's no vortex effects. In summary, the classic airfoil theory gives us a great baseline to go off of on how it generates lift, but ultimately it cannot accurately predict the Samara's 3D vortex-driven aerodynamics. So with this in mind, we took it to a bio-inspired rotating device where we constructed a baseline paper rotocopter using the Exploratorium design. Our dimensions are here as followed, and we performed 5 trials with a drop height of 10 feet, and we recorded descent time and its rotational behavior. We use consistent test conditions with the same drop location, same person drop in, and same person timing to reduce some of those human errors. And both models are here as shown. We then applied our knowledge with the Buckingham pi theorem and scaling laws to our 2 times scaled design. We constructed a 2 times scaled design by doubling all of our linear dimensions. We used the same material to preserve density and material properties. And our scaling prediction was that with a larger characteristic length, that would result in a higher Reynolds number. We also expected a faster descent for the 2 times model. We performed 5 additional drops, repeated the same process for this model. Here, our data shows us that the 2 times scaled model, which is the line in orange, has a higher descent time than the baseline model. This is not something that we predicted. The 2 times model descended slower, not faster, which contradicted our prediction. Our scaling theory was not wrong. Our assumptions were just incomplete. There's real world effects that dominate the behavior, like increased blade area, greater paper flexibility, and a higher moment of inertia. There are some potential error sources, a slight variation in drop height, human reaction time on the stopwatch, and differences in how we fold the models could affect our results. We tried to reduce error as much as we could by following these steps of same person drop-in and timing all the trials, same drop height of 10 feet, and same indoor location to get rid of air resistance or any outdoor wind errors, and same folding method for each model. To conclude this project, the Samara seed was a great demonstration of auto rotation. Mass and wing geometry controlled descent speed, and larger wings generate more lift. We were able to apply our knowledge of the Buckingham pi theorem and airfoil theory to compare it to our experiment. We showed that real-world factors like flexibility, inertia, and 3D flow cause the deviations that the Buckingham pi theorem and airfoil theory cannot accurately predict. We then added it to a bio-inspired application with paper rotocoppers applied to Samara Insights. Scaling tests revealed that the limits of idealized prediction. And why is this relevant? Natural auto-rotation principles inform design of small drones and monocopters, showing how simple natural mechanisms inspire advanced flight systems. Thank you.